I figured out how to fix the Mathematica thing. If I just been a little calmer and spent 5 to 10 seconds thinking about it, I think I could have realized how to fix it in the last lecture. The problem was that I wanted x to be the variable of this function, and that variable shows up here, but it's also showing up here and here and here, and I really don't want it showing up there, so Mathematica is kind of trying to plug the variable in there. So I should use some different letter, maybe like x0 instead of x. There. And now it does work, actually. Plot it. So here we have the example. The blue graph is the graph of 1 over 1 plus x squared. The red graph is a Taylor polynomial, first of degree 0, just equals 1. Then of degree 2. The red graph now is the graph of 1 minus x squared, parabola. Then of degree 4, although you don't see it until n is 4. Then of degree 6, when n is 6. Then degree 8, when n is 8. The odd ones don't change because there was no odd power in there. Playing this, you can see it converging to the blue graph on the interval from -1 to 1. Let's check the other facts. I'm not going to bother graphing, but let's check the formulas. If f of x is the arctangent function, what, for example, is P7 of x? P7 of x. There it is. Does it match what I have on the board? Here. They're practically right on top of each other there. Pair this with that. It matches. And how about that other function over there? Let's see. Where I differentiated term by term, make a negative 2x up here, and make the 1 over 1 plus x squared be squared. Pair this with this. Coefficients for the odd powers of x, -2, 4, -6, 8, -10, 12. It's a match. That's kind of a strange function, though. A simpler function would be to just have a 1 up top instead of a -2x. 1 over 1 plus x squared squared, or if you prefer, 1 over 1 plus x squared quantity squared. The series for that can evidently be found from this series by dividing everything by -2x. Because this was the series for this function that had a -2x up there instead of a 1. So if I divide everything by -2x here, I should get the series for this. In other words, it should be 1, -2x divided by -2x is 1. 4x cubed divided by -2x is -2x squared. -6x to the 5th divided by -2x is plus 3x to the 4th. The next one would be plus 8x to the 7th divided by -2x would be minus 4x to the 6th, etc. Let's see if that worked. Compare this with that. It's working. These facts are true, by the way, on the open interval from -1 to 1, not at the endpoints. When you integrate, you can sometimes gain an endpoint, but when you differentiate, you can sometimes lose endpoints, although with the geometric series, we did not include the endpoints to begin with anyway. Which brings up another question. That's 1 over 1 plus x squared quantity squared. Can I figure out the same answer by squaring that? The answer is yes, and let's do it. Squaring an infinite series? Are you kidding? No, I'm not kidding. And it's not as hard as it sounds. So I should also be able to find the series for 1 over 1 plus x squared squared by squaring this thing, multiplying it times itself, which again is not as hard as it sounds. Here's the technique. And this technique is going to seem a little fishy, like, can you really do this? But we are trusting that it can be done, at least in the interior of the interval of convergence. Take each term on the left and multiply it by every term on the right once. 1 times all these terms is all these terms. It's 1 minus x squared plus x to the 4th minus x to the 6th, etc. Then go to the next term over here, negative x squared, and multiply it times all these terms once. Negative x squared times 1 is negative x squared. Put the answer below the other negative x squared like that. Negative x squared times negative x squared is positive x to the 4th. Put it below the other x to the 4th. Negative x squared times x to the 4th is minus x to the 6th. Put it below the other one. Go to the next term, x to the 4th. Multiply it times each term over there once. X to the 4th times 1 is x to the 4th. Put it below the other x to the 4th. X to the 4th times negative x squared is minus x to the 6th. Put it below the other ones. Etc. Negative x to the 6th is the next term. Multiply it times every term over there. The first multiplication will give you negative x to the 6th, then I go, etc. What we really have here is an infinite sum of infinite sums. Oh, how? What? Don't worry about whether this is okay or not. We're waving our hands and saying it's okay without proof. Add this up. Column-wise. 1. 2 of those, minus 2x squared. Can you see it down here? Mm-hmm. 3 of those, plus 3x to the 4th. 4 of these, minus 4x to the 6th, etc. We're getting the same thing as we got up here. It worked. I think that's so incredible. Different methods giving the same answer, math is consistent. Right? I think that's a pretty incredible thing. Can you divide infinite series? Yes, you can. Though it is harder to find two things. It's harder to find a pattern for your terms when you divide. And it's also harder to figure out the interval of convergence. We will do a long division here to find an infinite series, but we need 2 other facts first before we're going to do this example that I'm talking about. The 2 facts that we're going to need before we can do a long division to find a new series is we need to know the series for sine of x and cosine of x, and then doing a long division will help us find the series for tangent of x, since tangent of x is sine of x divided by cosine of x. The equations I'm about to write down for sine of x and cosine of x are part of the many wonders of the world, or you might even say wonders of the universe. That these equations are true is pretty amazing. They can be derived as Taylor series formulas for sine and cosine using the formula that I erased that involves the derivatives. The kth derivatives divided by k, plug in 0, in this case a is going to be 0, and divide by k factorial. They can be derived that way, and you should be able to derive them that way. That doesn't prove they equal sine and cosine, but they do. We will see why that's true, hopefully later this week or early next week. Sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. So we get an alternating in sign, odd degrees over corresponding factorials expansion. Sine of x is an odd function, so maybe it shouldn't be surprised that we get a bunch of odd degrees. Cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So it has a similar kind of pattern, except it's all even powers instead of odd powers, which maybe shouldn't be a surprise since the cosine function is an even function of x. It turns out these series converge for all x. The interval of convergence is the entire real number line. The radius of convergence is infinity. You could check that with the ratio test. It's not too hard. Moreover, they equal these functions for all x as well. That's even more amazing. These are true for all x. Just an amazing, amazing fact about the universe that we live in. But those equations are true. I can now use these equations to find, say, the first 3 non-zero terms of the Taylor series for tangent of x when a is 0, using the fact that tangent of x is sine of x divided by cosine of x. I'll put a question mark next. So I'm going to take this infinite series and divide by this infinite series. It's not as hard as it sounds. If you do it in a long division setup, put the series for sine of x inside here, and I'm also going to simplify the factorials. 3 factorial is 6. 5 factorial is 120. That's all the further I'm going to go. For the cosine, I'm going to put it over here. 2 factorial is 2. 4 factorial is 24, etc. Then you ask, what do I need to multiply this lowest degree term here, 1, by to get the lowest degree term there, x? Well, I need to multiply it by x. So x becomes the first term in the Taylor series expansion. Now, multiply that x times every term here, and put the answer down there, and then subtract. X times 1 is x. X times x squared over 2 is x cubed over 2. X times x to the 4th over 24 is x to the 5th over 24, etc. Now subtract. Long division. X minus x is 0, that goes away. Negative x cubed over 6 plus x cubed over 2. 2 minuses making a plus. Let's see, 1/2 minus 1/6 is going to be what? 2/6 or 1/3? 1/3 x cubed. 1 over 120 minus 1 over 24 is the coefficient of x to the 5th. Getting a common denominator of 120 gives you negative 1/30th for the coefficient of x to the 5th after subtraction. All right, not done. We found the first non-zero term. We're going to find 2 more. What do I need to multiply 1 by to get 1/3 x cubed? I need to multiply it by 1/3 x cubed. That's the next non-zero term. 1/3 x cubed times 1 is 1/3 x cubed. 1/3 x cubed times negative x squared over 2 is negative 1/6 x to the 5th. And I won't bother going further. Subtract. Those cancel. Negative 1/30th plus 1/6 is going to be 5 minus 1 over 30. 4/30ths or 2/15ths. 2/15ths x to the 5th is what I'm writing down here if you can't quite see it. 2/15ths x to the 5th. And that'll become the next term. 2/15ths x to the 5th. And I can just say dot, dot, dot after that one. That's the first three non-zero terms. Again, it's not clear what the pattern would be, if there is a pattern for the coefficients. It's also not clear what the interval of convergence would be. The interval of convergence for these was the entire real number line. It can't be for tangent. I mean, you've got vertical asymptotes at pi over 2 and negative pi over 2. Perhaps the interval of convergence is negative pi over 2 to positive pi over 2, but that's not obvious that that will happen. Is it right? Let's have Mathematica check it. So here I'm going to put the tangent function in here. And I guess we're going to go ahead and calculate P7, so we'll calculate more non-zero terms. One more, in fact. Coefficients, 1, 1/3, 2/15ths. We're right. The next one is 17 over 3/15. By the way, there is a built-in Mathematica command to do this. It's called series. You can look up the syntax in the documentation center. Series. The syntax is like this. Series, your function. X is centered at 0 in this case, and then essentially the first 10 non-zero terms. So if I do that, copy and paste that in here, and replace x of x with tangent of x, go up to 7 here, I get the same thing. It adds on what's called big O of 8, which basically means 8th degree and higher are the other terms that are missing. That's basically what that means. That's a command that you can use to check the answers too. You can do more. You can use, for example, the series for sine of x to find the series for x squared sine of x cubed. How? For the series for sine of x, which is true for all x, replace the x's with x cubed. Then multiply the answer by x squared. Replace all those x's with x cubed. Like this. And then simplify. X squared times x cubed is x to the 5th. X cubed cubed is x to the 9th times x squared is x to the 11th. X cubed to the 5th is x to the 15th times x squared is x to the 17th. I think the next one will be x cubed to the 7th, x to the 21st times x squared would be x to the 23rd. Oops, that's not over 17 factorial there, by the way. Mistake. 5 factorial. And this is over 7 factorial, etc. Let's check it. Let's check it with series this time. X squared times sine of x cubed, and we want to go through at least the 23rd power, so I need a 23 here. And do we have a match? Yeah, because 5 factorial is 120, 7 factorial is 5040. It's a match. So substitution, multiplication like that is another trick you can use. Another series you should remember for the future. These are true for all x. There's a series that's kind of similar for e to the x. that is also true for all x. In fact, it's essentially these combined with all plus signs. This equals e to the x for all x. Another amazing fact that you should know. And you should know these facts until you're 80. Okay? You should remember these things. They're part of just general cultural knowledge that people should have. I mean, I know not everybody has it. You might even say 95% of the people out there don't have that knowledge. But you really should, everybody really should know these facts. Interesting, I'm not deriving these at the moment, but interesting that these are true and also that they're kind of related to each other. I said you can get the series for e to the x by essentially combining the series for sine and cosine, adding them sort of, except make all the minus signs pluses. Interesting. We will see on Wednesday that if you think about this in the context of complex numbers, with the imaginary unit involved, I squared equals -1, I is the imaginary unit, that there is a relationship between these equations. That's one of the most beautiful things in the universe. It leads to the most beautiful equation in the universe. I'm going to show you an animation seeing the Taylor series, say, for the cosine function, approaching the cosine function. I showed this animation to a former student, and well, I won't claim it'll do the same thing to you that it did to him. But he said this animation that I showed him changed his life. I'm serious. He told me afterwards he did. That it changed his life. Let's plot this, say, from -10 to 10. Let's let n go up to 20. Okay, you want something that's going to change your life? Oh, no guarantees. Here we go, ready? 1, 2, 3. Bird flapping its wings. Better and better approximations to the cosine function with finite Taylor polynomials. It helps you believe that the infinite Taylor series does equal the cosine function over the entire lambda line. Let's make it even bigger window here. Let's go -30 to 30. And let's go up to, say, 40 there. I'm not sure how slow it'll be, but let's do it anyway. Oh, that's fast. There we see the convergence of the Taylor polynomials to the cosine function. Is it changing your life? Well, okay. I don't know if I should bring that up or not, but a student from, it was like 15 years ago, said it changed his life. Because it got him actually intrigued in math, whereas he wasn't before, or something like that. There is another example we need to look at here. Another class of examples. And then we'll end class after that. Another formula worth memorizing, maybe for your entire life, is called the binomial series. And in its simplest form, it helps you expand things like this. Now, you should recall from your pre-calc days, or maybe even earlier, if p is 2 or 3 or 4 or 5 or 6, there's a binomial theorem involving Pascal's triangle and binomial coefficients, which are combinations that help you do this expansion. And what I'm about to write down does work in that case, though it doesn't give you an infinite series in that case, it truncates. If p is some other number, including fractions, or even irrational numbers like pi, what I'm about to write down is still true. This equals 1 plus p times x plus p times p minus 1 over 2 factorial times x squared plus p times p minus 1 times p minus 2 over 3 factorial times x cubed, plus I'll write one more non-zero term here, p times p minus 1 times p minus 2 times p minus 3 over 4 factorial times x to the 4th, etc. This converges when the absolute value of x is less than 1 if p is not equal to some positive integer, 1, 2, 3, 4, 5, 6, etc. Or 0 for that matter. If p is one of those numbers, then it's really a finite sum. It's not an infinite series, and there's no issue about convergence. It does converge for all x. In that case, it converges on a smaller interval when p is not one of those. Okay? You can still do this when p is a positive integer, but it's more trivial actually. It simplifies. For example, if p is 3. All terms this point and on go away if p is 3 because you get p minus 3s in the numerator. So this is true, and it's something you should try to remember, even though you can use a no-coverage test. And learn how to use in various situations, including some situations that seem pretty tricky at first. For example, the following function, f of x, is, say, 1 over the cube root of 8 plus x. Is actually an example where you can use this, but it's not obvious how. It's good to, first of all, factor 8 out of the cube root, or out of the thing inside the cube root, and then use the fact that the cube root of the product of two things is the product of their cube roots to write this. And I made it an 8 on purpose so that the cube root of 8 is simple. 1/2 is 2. So this gives me 1/2 times 1 over the cube root of 1 plus x over 8, which is the same thing as 1 plus x over 8 to the negative 1/3 power. Now this thing, 1 plus x over 8 to the negative 1/3 power, is pretty similar to this, except it's an x over 8 instead of an x. That's okay. You just use this formula with x over 8 in place of x. P is negative 1/3. The 1/2 is just in front. It just gets carried along, and then we can multiply it through at the end. So this is going to equal 1/2 times, in parentheses, look at this formula on the board, 1 plus p times x. P is negative 1/3. X is not x, it's x over 8. I'm replacing the x here, which is just a symbol that must be less than 1 in absolute value, with a new symbol, x over 8. That must also be less than 1 in absolute value, so x itself must be less than 8 in absolute value. Let's get a couple more terms. Plus negative 1/3 times p minus 1 is going to be negative 4/3 over 2 factorial times x over 8 quantity squared. The next one's going to be negative 1/3 times negative 4/3 times negative 7/3 over 3 factorial times x minus 8 quantity cubed, etc. This is going to be true if the absolute value of x over 8 is less than 1, which is equivalent, this is an if here, that's equivalent to the absolute value of x being less than 8. Now it's just a matter of simplification. We have time to simplify. think I will. Multiply the half through, you're going to get a half. Times, let's see, 1/24 x there, minus sign, and also a half gives you minus 1/48 times x. The next one's going to come from here and also multiplying by a half, plus sign. Two minuses are going to make a plus. We will get a plus here next. Plus what? Let's see. 2 times 2 is 4. 8 squared is 64. The 4, on top we have 4 nines. That times that. And the bottom we've got 64 times 4, 256. What will that be? That'll be, let's see, I can reduce a little bit. Looks like 9/64. Oops, no, sorry. Not 9/64, but 1/9 times 64 is what this would simplify to. And that would be 1/576, I think. So if I've not made a mistake, this next coefficient is 1/576 and x squared. I won't bother with the next one. It would be a minus because I've got 3 negative signs. And this is positive. So if I've not made a mistake, that's the first 3 non-zero terms for the Taylor series expansion of this when a is 0. A is 0 with these examples. You can do non-zero a's, but the most common thing to do is a is 0. We only have powers of x, because x minus a would be x minus 0, which is just x. That's the most common thing to do. Okay, so that's something else you'll get practice with. We'll see you on Wednesday.